So the first problem in chapter 8 that I got a question on was problem number 70. So problem number 70 from chapter 8. In this problem, we're told we have a 900 kilogram automobile that accelerates from 0 to 80 kilometers per hour in 7.6 seconds. We're asked to find the initial and final translational kinetic energies of the automobile, and we're asked to find what is the average power delivered to the engine in this time interval. They tell us to express our answer in horsepower, and in the instructions, I actually tell you to just leave that in watts. So the first step is to write down everything we know. We know the mass of the car. They give us that is 900 kilograms. We know that the initial velocity is 0 kilometers per hour. And we know that the final velocity is equal to 80 kilometers per hour. And I'm going to go ahead and make my life easier and just right ahead convert this into meters per second so I can get into SI units. So that's going to be 1,000 meters in 1 kilometer to get the kilometers to cancel out, and then 1 hour is 3,600 seconds to get the hours to cancel out to end up with meters per second, and I get 22 meters per second when I do that math in my calculator. First question we're asked is, what are the initial and the final translational kinetic energies of the automobile? So to do this, we need to know what the equation is for kinetic energy, and we should know that that is equal to 1/2 the mass times the velocity squared. So my initial kinetic energy is 1/2 my mass times my initial velocity squared. And now I can just plug in all the numbers that I know. 1/2 times my mass of 900 kilograms times my initial velocity of 0 meters per second. And I get that the initial kinetic energy is equal to 0. Then I'm also asked to find the final kinetic energy. So I can do the final kinetic energy is equal to 1/2 mass, and this time I'm doing my final velocity squared. So my kinetic energy final is 1/2, and I plug in my mass of 900 kilograms times my final velocity of 22 meters per second squared. Plug all this into your calculator, and you will find that the final kinetic energy is 2.18 times 10 to the 5th. And since this is all SI units, the units of that are going to be joules. So I can circle my nice little kinetic energy answers. I have both of those. Now I've minimized everything. We're still working on the same problem, and now we're going to move on to part B. In part B of this problem, we're asked to find the power. And I know that power is equal to work over change in time. I was given the change in time that this car is accelerating during is 7.6 seconds. So now all I need to do is find the work. And I know that work is equal to the change in kinetic energy. This is the work energy theorem. So the change in kinetic energy is the final kinetic energy minus the initial kinetic energy. And I can take my answers from part A to find that the work is equal to the final kinetic energy, 2.18 times 10 to the 5th joules, minus my initial kinetic energy, 0 joules. And I find that my work is equal to 2.18 times 10 to the 5th joules. And then I can take that and I can plug it in with my time to get power is work divided by time. Plug in my numbers, 2.18 times 10 to the 5th joules, divided by my change in time of 7.6 seconds. Go ahead and put that into your calculator, and you should get the number 2.9 times 10 to the 4 watts. And there you go, problem number 70. The next problem in chapter 8 that I was asked about was problem number 73. So let's move on to number 73, where we have a constant force of 40 newtons that is applied to a body as the body moves uniformly at a speed of 3.5 meters per second. So I know that there's a force that's equal to 40 newtons, and I know that that force is applied at a speed of 3.5 meters per second. The force does work on the body at a rate of 90 watts. So I'm doing work on this body at a rate of 90 watts. So when I'm doing work at a rate, that's essentially work over some time, and we should know by now that that is going to be equal to power. So my power for this is going to be equal to 90 watts. And I can know that again by doing dimensional analysis and looking at the units. If I have watts, then I know that I'm talking about power. Then we're asked to find what is the angle between the force and the direction of motion of the body. So what I'm doing here is I'm applying some kind of force. I'm pushing something at some angle, but it's actually moving in a slightly different direction. It's moving at some velocity in some other direction. So there's an angle between these two. And I can figure out that angle if I look at all these things that I know. Here's where we can talk about a good strategy for physics problems. If you have no idea what else to do, you write down all your unknowns. We have a force, we have a velocity, and we have a power. And then you can look basically at your chapter summary and see what kind of equations you have. And we have an equation that relates force, velocity, and power. The definition of the power delivered by a force is equal to F dot V. And this dot represents the dot product, which we should remember back from the very first 1 or 2 chapters where we talked about it. And the dot product tells us that power is equal to F times V times the cosine of the angle between the two. And now I can see that I have this angle in here. I have a theta. That's the theta that I'm looking for, the theta that's between the force and the velocity. So I can solve this for theta. I divide both sides by FV, and that'll give me P over F times V is equal to cosine of theta. And then if I want to solve for theta, I need to take the inverse cosine of both sides. So I get that theta is equal to the inverse cosine of P divided by F times V. We can minimize this down a little bit and plug in all of our numbers. Theta is going to be equal to the inverse cosine of my power, which is 90 watts, divided by my force, which is 40 newtons, times my velocity, which is 3.5 meters per second. And we can just plug this into your calculator. Make sure your calculator is in degrees if you want the answer in degrees, and we will find 50 degrees. If you get a slightly different answer, if you get a vastly different answer, your calculator is probably in radians, and you can convert into the 50 degrees by multiplying by pi over 180, or you could just change your calculator mode to degrees. So that's problem number 73. The last question in Chapter 8 I was asked about was problem number 90. So let's do Chapter 8, problem number 90. And in this problem, we have power that's being supplied to an electrical circuit that decreases exponentially with time according to the following equation. P is equal to P naught, some initial power, times the exponential function e to the negative t, which represents time, divided by tau. And they give us that P naught is equal to 2.0 watts, and tau is equal to 5.0 seconds, and these are both constant. And what they want to know is the total energy that's delivered to the circuit in 2 different time intervals. We want to know the energy delivered between 0 and 5 seconds, and we want to know the energy delivered between 0 and infinity seconds. So what we need to do is figure out how our power and work related to each other. And if we go to our chapter summaries, we can find that power and work are related by the integral. The work, or the energy, remember work and energy are the same thing, comes from the work-energy theorem, is equal to the integral between two different times, time 1 and time 2, of the power integrated over the variable t, over time. Okay, so if we keep this equation in mind, we can take the equation we're given for power and we can plug it in down here and we can start to solve this. We know work is equal to the integral from t1 to t2 of p naught times e to the negative t divided by tau, integrated with respect to time. Since I'm integrating with respect to time, one of the nice things I can do is I can bring my variable p naught out front, because there's no t's in that p naught. It's just a constant, it's a number, so I don't have to integrate over that. So now I have work is equal to the integral from t1 to t2 with the p naught out front, e to the negative t divided by tau, integrated over time. And now all I need to do is integrate over this exponential function. So I need to know what the integral of e to the negative t over tau is. And to figure that out, you need to go to your equation sheets most likely and figure out what is the integral of e. And the integral of e will give you p naught times the actual exponential function. So when you integrate e to the negative t over tau, you just get e to the negative t over tau, negative t over tau, and then you need to divide by negative 1 over tau. Divide by the derivative of the exponent that you're raising your exponential function to. And then you need to plug in endpoints between t1 and t2. So we have a general solution here, and we can write out this general solution a little bit more explicitly as work is equal to p naught, which is 2.0 watts, times e to the negative t divided by tau, which is 5 seconds, all divided by negative 1 over 5 seconds. And I need to evaluate that at two different times, t1 and t2. So now I have a general equation that I can use for part A and for part B. For part A, my t1 has to be 0 seconds, and my t2 has to be equal to 5 seconds. So I can plug these in. I can get work is equal to 2.0 times e to the negative t2 over 5 seconds, all divided by negative 1 over 5, minus 2.0 times e to the negative t1, the initial time, over 5 seconds, divided by negative 1 over 5. So I'm just plugging in my numbers. Now I can evaluate at my endpoints. I can plug in my 5 for t2. I can plug in my 0 for t1. Make a little bit more space so that we can do that. And I plug in to get, for part A, work is equal to 2.0 times e to the negative t2, which in part A is going to be 5 divided by 5, all divided by negative 1 over 5, minus 2.0 times e to the negative t1. And t1 in part A is 0. So e to the negative 0 over 5 seconds, all divided by negative 1 over 5. And this is pretty much your answer. You can plug these into your calculator. E is a function that will actually evaluate. E could give you a number, but you could just leave your answer as it is right here. That would be perfectly fine. You follow the same exact approach for part B. Part B, we're asked for 2 different times. I'm going to move this up and out of the way a little bit. And then we'll do part B. Part B, we take our same equation. Work is equal to 2.0 times e to the negative t2 over 5 divided by negative 1 over 5 minus 2.0 times e to the negative t1 over 5 divided by negative 1 over 5. And now I need to plug in my new limits. In part B, my t2 is my final time, which is infinity, and my t1 is my initial time, which is still given to us as 0. So I plug in those two values. Work equals 2 times e to the negative infinity over 5 over negative 1 over 5 minus 2 times e to the 0 over 5. That'll be negative 0 over 5 divided by negative 1 over 5. And here I need to do some thinking. I need to think a little bit. So if I take e and I raise it up to the negative infinity power, even if I divide infinity by 5, it's still a very, very large negative power. If I raise a number to a very large negative power, I end up with 0. And then I can subtract off my 2e to the negative 0. If I raise any function to the exponent of 0, then I end up with 1. So that should just give me a 1, and I get 2 divided by negative 1 over 5. And here we can actually evaluate these numbers. If I take negative 2 divided by negative 1/5, I end up with 10. And the units there are the units of work, so I end up with 10 joules. And there you go.